Okay, we're back and we're going to do some enum. In particular, what about objects where we cannot use Gauss's law? These would be things like rings and sticks with ends. Those are the two classic types that we've done in class. If you can't use Gauss's law, if you have ends and edges and corners and things like this, we're pretty much stuck with using the fundamentals. That is, we have to think of objects as they really are when they have charge, and that's a bunch of point charges. That's okay though, because point charges are the one thing we know how to do exactly. Where we know electric fields go as kq over r squared, and we know that potentials go as kq over r. So the example I want to do here is a stick. These tend to be a little bit trickier, and we'll be trying to find the electric field at some point down here on this axis that cuts the stick in half. So as we need to do, we're going to think of breaking the stick into a bunch of little point charges, a bunch of little dq's. And so for example, this blue one here, it's shooting an electric field out of it along that line. It's the radial vector, and so it's going to be pointing on here at some angle, and that'll be the distance between the charge and the point. So right away we can get the total little field, we'll call it dE I guess, from that point charge, and it's following kq over r squared. It's going to be our constant times dq, and that distance then, r squared would be y squared plus x squared. Okay. And the reason we do this on the bisecting axis is because there's an equal amount of charge on the other side, which is shooting an electric field down at that angle, and so we can see that the x components are going to cancel out. So in this case, what we're really after is just the y component. And how do we do that? Well, like we always do with vectors, if we know what this angle is right here with that vertical line, which would be the same as this angle in this bigger triangle, to pick out just the downward component, we'd have to multiply it by cosine of that angle. Okay, and from our picture, let's rewrite this cosine. Let's see, it looks like cosine is going to be y over r. So I'm going to plug in y over the square root of x squared plus y squared, and so in our denominator we'll have that quantity to the 3/2 power. So this is one of the contributions from one of the little point charges. Okay, well that's not the total. How do you get the total? Well, the total field, pointing straight down in the y direction, we get that when we add up, or integrate, all of the little contributions. Okay. So our integral starts to look something like this, where we just plug in what we have. Okay. And you might look at that and say, okay, well, how do we evaluate this integral? Well, it's not quite as easy as it looks. Unfortunately, dq is not the variable. If you think about it, if you break this into a whole bunch of little slices in either direction, and ask the question, well, what's different about each of those little dq's? It's the x value. So, since x is our variable, the only way we can evaluate this integral is if we put a dx inside there. Okay, now, this is pretty similar to what we did and do in mechanics when we have moments of inertia and break things into little masses. We can make use of a little trick as long as you have a uniform distribution of charge along the length of that stick. Then we would figure that this ratio of the charge per unit length, the total charge over the total length of the stick, is a constant. It's like a density. We call it a linear charge density. And so that would mean it could work for the whole, and it could work for a piece of it. So if dx is the little bit of length of one of our little chunks of the stick, this is our ratio that we can follow, and therefore we can write dq in terms of dx. Okay, this is what we're going to substitute into our integral. So in the end, the integral that we have is k times y times this dq, but now we substitute in total charge over total length times dx, all over the distance, that's the r, to the 3/2 power. And last but not least, we need limits on this integral. In order to add up all the chunks, we have to start at one end and keep adding chunks all the way to the other end. So we're going from x equals negative L over 2 to positive L over 2. Okay. The only thing I'll do is let's pull out constants. Let's remind ourselves what the constants are. K is a constant. That distance y is a constant. That's a fixed distance to the point we're looking at. Total charge and total length are constants. And then we have to keep everything else in there. So this ends up being the integral we have to evaluate. Now I'm actually not going to do it here just for time's sake. It's probably a trick substitution. Some people I know would pull out their inspires and type it in. Otherwise you can look in the back of our book. And there's an integral table in one of the appendices and write down the answer. I'm not worried about what the answer is. All I want to do here is demonstrate the process, the thinking, the fundamentals behind all this. It can be tricky trying to set up your own integrals, but fundamentally, don't forget, all we're doing is breaking it up into point charges. That's what we know how to do. Fields are the more complicated ones because we have to find components. So we get a little trickier integral than if we're doing voltage. Okay. So, and last but not least, this is where we have to use this ratio, this charge density idea, in order to evaluate the integral. So there's a little bit there. It's not as easy as it might seem on paper, but in the end, we get something that we know that we can solve, and we can actually find an answer to this. So I hope this helps. Until next time, we'll see you later.